Hello everyone, my name is Frans and welcome to Physics 101. Today I'm going to show you how to draw, or rather how to draw in simple ways, draw free body diagrams. So for example, this is part of Newton's second law. You can also use it when you do work, energy and power. So let's just call it free body diagrams. This is very much important when you come to those two topics that I've just mentioned, because if you are not able to solve, or rather to draw correct free body diagrams, when it comes to calculations, if you do not get them correct, you're as good as dead, because you won't be able to get correct answers and then be able to formulate, or rather create correct formulae and equations rather for questions that will be following after drawing the free body diagrams. Sometimes they will not say to you, or rather ask you to draw this free body diagram. They will just say the definition and get straight to the point. So it will be up to you to draw them on a different page, or maybe on your question paper, such that you become able to have your things laid out and clearly fixed. So that's where I come in. For example, firstly, I'm going to start with free body diagrams of objects on a horizontal surface being pulled on a straight horizontal surface. Let's say, for example, we are given an object like this. You see? So maybe they are saying this object is going to the right. What is going to happen is this. Where the object is going, you have to, maybe they will say this is force applied of a certain magnitude. For one, you need to know few things. An object on a horizontal surface has normal force. It has four forces. Number one is normal force. Number two is weight, or force due to gravity. Force due to gravity. And then if this is a rough surface, it has frictional force. Frictional force. And of course, we have the fourth one, which is the applied force, or force applied. So, in other words, this object is going to have four forces on it, which is the ones that I've just mentioned, or rather stated here. So how are we going to draw the free body diagram? We are going to utilize a dot like that. You see? And then where the object is going, in the direction that the object is going, you're going to draw that force applied. If the object is accelerating in that direction, or maybe is being pushed and it is moving in that direction of the force applied, that simply means when you draw the free body diagram, the length of the force applied has to be longer than any other force that will be there on the free body diagram, to show that the object is basically moving in that direction. I'm going to show you where this particular thing comes from, whereby we're going to say the length of the force applied has to be longer than any other length of the forces that I mentioned here. And then for the weight and the normal force, the forces have to be equal. You see? And then the frictional force, it has to be, yes, it can be long, but not longer than the force applied. So meaning this is going to be our force applied, which is going to the right, and this is going to be our weight, or you can just say F subscript G. G means force due to the gravitational acceleration, or rather to gravity, and then the normal force, or force normal, as other people like to call it. And then here we have the Fk, which is basically Fk to show that the object is moving, which is the kinetic frictional force, from the word kinetic, meaning something that is in motion. Cool. Now, I said prior, I'm going to show you why this particular force, which is a force applied, has to be basically greater than this particular one. which is the kinetic frictional force. Let's go back a bit to grade 10 and 11 when we were dealing with vectors and scalars, or rather this particular part, vectors. When we draw vectors and they say to you there is a 10 Newton force being applied to the right, a 10 Newton force to the right, we will just call it just force to the right. And then I'm going to have a point of departure of it here. And then a 6 Newton force applied to the left. 6 Newton force applied to the left. As you can see, this is 6 Newtons, and that is 10 Newtons. What you are going to do is this. You're basically going to add, they are going to say to you, find the resultant vector. The resultant vector of these things is going to be, force to the right. I'm just going to write it as FR, force to the right, and then plus force to the left. As you can see, these two things are going in opposite direction. The other one is going to the right, and the other one is going to the left. In other words, what you can do basically now is to say the one that is going in that direction, there whereby it has a greater magnitude, is going to be the positive one. So basically we can say the one going to the right is positive, and then the one going to the left is going to be our negative force. What is this thing telling us? We are going to say positive 10 newtons minus 6 newtons, which will ultimately give us what we now have as 4 newtons. And since, well, this is a force, it is a vector quantity, it has direction, 4 newtons to the right, which basically has helped us to go back here where I said to you, the force applied in which the direction, or rather the object is going, has to be greater than the frictional force, because vector quantities appears to be this way, or not appears, happen to be in this particular magnitude. I mean, a scenario whereby a force applied is greater than the frictional force, hence the object, it is moving. I hope this makes sense, and I hope it's clear right now. And then if this particular thing makes sense, that simply means we understand this particular concept of forces that are moving on horizontal surface. And then when they move on horizontal surface, there is no angle whatsoever between the force and the surface. And then all the forces, and these two forces are balanced. And then these ones, obviously, they are going to cancel each other out. Ultimately, we're going to have something like the resultant force. I hope that makes sense. Now, if I were to erase this particular thing to get our second part of this particular thing. Yes. Now, on the very same horizontal surface, what we can find is a force that is being pulled at an angle. We have a horizontal surface here, and then we have a force that is being pulled at a particular angle, or rather an object that is being pulled at a particular angle. Let's say this angle is going to give us, we're going to call it theta for now. And then by calling it theta, this is going to be this particular object. Now, the question will come and say, draw a free body diagram. So from here going onwards, I'm going to do something. I'm going to show you free body diagram of calculations and free body diagram of marks. I'm going to say here, I'm going having free body diagram of marks, and then here, calculations. The same is true also, all the things that I listed prior of the force applied, frictional force, normal force, and weight are going to apply here. They're going to apply exactly here also. So before that, I just want to talk about this particular force, and then let me just formulate something like a right angle triangle here, such that we become able to understand what is it that I'm going to do. I'm going to use a different color, which is blue. So as we can see, this is the y, meaning it's vertical. So I'm going to call it Fy. And this one, which is the horizontal, I'm going to call it Fx. And then the red one, which is the force applied, I'll just call it force applied. In other words, we basically have what we call components of forces. It also takes us back to the vectors whereby we had components of a vector. So here what we're going to do is that we need to be able to understand, or rather to find the formulas of Fx and Fy. How do we find that? We have a right angle triangle. How do we make sure that we find correct, or rather be that you forgot how to do these things, you can derive them. That's where the beautiful part of mathematics come into place. Derivation of a formula. Now, we're going to use trigonometric ratios to derive this particular formula. Let's try with Fx. We have hypotenuse. I'm going to say hypotenuse, which is going to be our force applied. And then we have the opposite of angle theta. Opposite is Fy. And then we have the adjacent of angle theta. Adjacent, the side below the angle. It's going to give us what? Fx. Now, where does this trigonometric ratios enter, and how are they going to help us? We will be saying, if I want cos of theta, it is going to give us what? Let's do this. Cos theta is equals to adjacent over hypotenuse, and then sine of theta is going to give us opposite all over hypotenuse. Now let's utilize those two realistic mathematics ratios of trigonometry. What is the adjacent side of the cos of the angle theta is going to be our Fx. I'm going to write Fx, and then hypotenuse, as I stated prior, it is our Fy. I'm going to write Fa, and then I want to make my Fx the subject of the formula, which takes us back to grade 10, whereby we learned how to do this particular thing of making something the subject of the formula. I'm going to multiply both sides by Fy, and then on this side, the left hand side, I'm going to have Fa, not y, Fy, Fa cos of theta, and then be left with Fx. Alright, doesn't look nice since when I want to make Fx the subject of the formula. Can just interchange and end up having Fx equal to Fa cos of theta. Now I have the vertical component of force applied. The same is true again. I want to find Fy. So I'm going to utilize this side and use the red color for Fy. So I'll utilize sine of theta. What is the opposite of the angle theta? It's going to give us Fy. And then what is the hypotenuse? Fa. Again, I'm going to multiply both sides by Fa, and I'll end up having Fa sine theta, which is equals to Fy. Again, I'm going to do that particular thing that I've done here, interchange. I'll have Fy is equal to Fa, sine theta. And now we have what we call what? The vertical component of force applied. By doing that, I've made our work easy. Now I'm going to show you what we basically need to do, which is what? The free-body diagram. Let's go back. For marks of this particular thing is they're going to say 4 marks, draw the free-body diagram. What you are going to do is this. You start with your beautiful dot, and then after having your beautiful dot, your force applied is going that side, you are pulling it there, right? And then remember, we have normal force going up, and then we have weight going down. And of course, maybe let's guess it's a rough surface, we are going to have a frictional force. Remember, with the issues of the length, frictional force has to be lesser in size than the force applied. I'm going to say force applied, Fk, normal force and weight. That's the free body diagram of mass. Now, and then the free body diagram that you are going to utilize for your calculations is the free body diagram that is going to show you the components of these forces. Basically, you're going to have your beautiful mark again here. All right. Let's write those that we know first. Please do not write the force applied first. I'll just put the normal force and then the weight and then the frictional force. Force normal, force weight, or rather weight. And then now, what is it that we must do? Care should be taken. The object is being pulled at an angle that is going up. That simply means the Fy, or rather, yes, the force, the vertical component of this particular force is going to go in the upward direction. I'll call it Fy, as I've already stated there. Some other books, they normally call it force horizontal. Vertical, Fv. It is still the same thingy. And then the object is moving to your right, so meaning the Fx, which is going to be the longest force, is going to be going to your right. This is how you do the free body diagram of calculations. Again, if you are given an object of this nature and then they are saying to you, you should draw the free body diagram, and you see 5 marks, that simply means that they are giving you an idea, or rather a picture of saying, break this force and make it have the components, which is going to give you all of these 5 forces. I hope that makes sense. And then that will be our lesson for today, the horizontal forces, and then the one that is being pulled at a particular angle. Thank you. See you tomorrow.